All right, so we are starting with problem 11. Make a couple of corrections. Sorry about the units on the table. So it did have SI units. Make sure you fix that. Put that in English units. So we have an insulated tank, and I've made an effort at trying to draw state 1 and state 2. This is very similar to a problem that we did before where we had a closed system and we had two compartments, and then we separated the partition or pulled out the partition that separated those two compartments and allowed things to mix. The only difference, I guess, really is just that it's English units instead of SI units. So we've got carbon monoxide and helium. We're initially given the volume, the temperature, and the mass of each of those components. We also know that the tank itself is insulated, that it's rigid, and that the total volume is 60 feet cubed. And then the gases are allowed to mix until an equilibrium state is attained, and we're supposed to find the final temperature and the pressure at the end. It says you can assume specific heats are constant. You can go through sort of a reasonable process of figuring out those CV values. The CV for helium is kind of hidden in your table, so yeah, the likelihood is I'm probably going to give you any CP or CV values that you need if they're hidden, or if it's not obvious what temperature to take them at. For example, here it's not really obvious because normally you would take those CV or CP values at the average temperature, and T2 is unknown, so you don't really know what that average temperature is. So just to keep things simple, I went ahead and I'm just going to give you the CV values for each of those. So the CV for carbon monoxide that you're going to use is 0.18 BTU per pound mole degree Rankine. I use that because I looked in table A20E and I said, well, I know the temperature is not going to be the average of these two temperatures, 960 and 520, but it's going to be somewhere in the middle. So, I don't know. Let's make an educated guess. It's going to be somewhere in there, and I based my my CV value on that. And then my CV for helium is 0.744 BTU per pound mole degree Rankine. That one's kind of hidden table A21 if you're curious. But yeah. Anyway, all right. Again, if it's not obvious how to get that CV or CP, you can't easily get it from A20, then you would expect me to give that value to you. All right, so I know I need to find T2 and P2. I'm going to start out by just plugging stuff into my table, and that way everything's nice and organized, and everything else just kind of goes smoothly from then on out. So the first thing that I'll get is maybe my masses, because I'm given that the mass, the carbon monoxide and the helium, I'm given that in the problem statement, so I'll go ahead and put that there. I can also go ahead and calculate the mass, so it's just the sum of those two things. I can also get the molar mass that's in table A1E. So carbon monoxide and helium are in there. And then I could just sort of work my way from the left to the right on that table and get the number of moles, right? 4 divided by 28.01, 0.81 divided by 4.003, and that'll give me the number of pound moles for each of those components. And then you can add those up, get the total number of pound moles, and from there you can calculate the mole fraction if you need it. So 0.1428 divided by 0.3427 would give you 0.4167, and then same thing for the helium. And then I'll go ahead and get the mass fraction as well, right? 4 divided by 4.81, 0.83, and so the other mass fraction has got to be 1 minus 0.83, so 0.17. All right, so I went ahead and did that, and now I feel like I've got a lot of flexibility on the equations that I decide to use when I have to look up ways to calculate delta U's or whatever the case may be. All right, so I'm going to first, I need to find T2, and a good place to start is by applying my first law. So let's do that. So I apply my first law. I've got a closed system because my system is everything that's in that tank, that rectangle there. Because it's insulated, I'm not going to consider heat transfer. Because there's no boundary work, I'm not going to consider work. I'm also not going to worry about kinetic and potential energy changes. And so that cleans up very nicely. Just a delta U is equal to 0. And then if I look on my equation sheet about how to calculate delta U for an ideal gas with constant specific heats, let's make sure that's exactly how it's written actually. Let's go look, sorry. Ba-da, ba-da. There we go. Yeah, there we go. Oops, not that guy. Let's get that guy. All right, so yeah, right there. There we go. And we're given the CV, so good to go. All right, so it's the sum of the masses of each component, and I've got those things, times CV for each component. I've got those things, and the delta T, which we'll get in just a second. I've at least got the initial temperature for each of those gases to plug in, so I should be good there. All right. So it's a summation for each one of those components. I've got carbon monoxide in blue, helium in red. Notice that T2 is for the mixture and the component are the same. So T2 for the carbon monoxide is the same as T2 for the mixture, for example. And then it's just a matter of solving for T2. I know all the values there except T2. I've got a value of 891 for that guy right there. So easy peasy. The other thing that I was supposed to find is the pressure at the end of that equilibrium process. So I need to find P2, and this seems like a good place to apply my ideal gas law. So N bar R bar T over the volume, or you could put it as M R T over V. Although if you do that, if you have M R T over V, then you're going to need to calculate that specific gas constant for your mixture, and this is a little bit extra work. So, and we already have the number of moles, so yeah, might as well use the easiest thing that's available to us. So, yep. There we go. I've got the number of moles. I've got my R bar. I chose 1545 just because the units were going to work out nicely. I used 891, which was the temperature that I calculated in part A. Volume, total volume is 60 feet cubed. And then, of course, I need to reconcile the feet. And actually, that's not 12 inches or 12 feet squared. That should be inches squared. And that will allow me to get things in terms of pound force per inch squared, or PSI. So, all right. So hopefully that was helpful. Let me know if you have any questions.